speaker is Daniele Micciancio, who my honor to be one of my first graduate students at MIT. And Daniele is a professor in UCSD, and he is really the world authority on lattices and lattice cryptography. And I also wrote one of the first, maybe the first book about this, right? It was your thesis about lattice cryptography and lattice-based algorithms. And Daniele made a very appropriate comment that before lunch we had quantum cryptography, and he's going to talk about post-quantum cryptography, which is quite appropriate. Again, we have a real treat in front of us. So, Daniele, thank you.
Okay, thank you for the introduction. Thank you for inviting. And yes, okay, so this goes scheduled after the pre-quantum, so now it's post-quantum. So I'll be talking about lattice problems and zero knowledge. And so I'll be talking about lattices and zero knowledge. So let me start with a brief introduction to both things. So lattices are mathematical objects that were that have been studied by mathematicians for quite a long time. They started being used for the construction of cryptographic functions starting in the mid-90s after a discovery of I-tide that there is a connection between the worst case complexity of lattice problems and average case complexity. An average case is what you need in cryptography, so that you get hard to break functions when you get your key chosen at random, while worst case complexity is a much weaker assumption that you can try to study and understand without having to worry about distributions on how the problems are chosen. So this opened up the possibility of building cryptographic functions from certain types of worst case assumptions, which also happened to be potential candidates for post-quantum cryptography. I mean, the term post-quantum cryptography didn't exist yet back then, but the Schnorr algorithm was already there. So people already knew that the kind of public key cryptography being used and still being used was subject to quantum attacks, and lattices offered a possibility to design a quantum proof classical crypto system, something that can be used with just regular conventional classical computers, but is not known to be breakable by quantum algorithms. Another discovery that got attention to these problems was the proof that SVP, the shortest vector problem, which I am about to define, is NP-hard, the standard notion of hardness used in complexity theory. And so this opened up the possibility of try to base cryptography on the minimal assumption that P is different from NP. And there is a gap between what you need for cryptography and what can be proved NP-complete. So both problems use approximate versions of SVP, of the shortest vector problem, and there is a gap between the factors for which one can prove NP-completeness and the factors which are required for cryptographic functions. And understanding this gap was one of the motivations of some early work on interactive proof systems and zero-knowledge proof systems for lattice problems. Now, the area of lattice cryptography substantially expanded after the introduction of the learning with errors problem by Regev, and then a few years later the proposal of the first fully homomorphic encryption scheme based on lattice problems, and today lattice cryptography is considered one of the main candidates for post-quantum cryptography. So on to lattices. What is a lattice? A lattice is a geometric object, is a set of points in Euclidean space. It's something similar to a vector space. It can be described by a basis. For example, in two dimensions you may give these two vectors, B1 and B2. And instead of taking all the real linear combinations of the basis vectors, you take only linear combinations with integer coefficients. So the result is a discrete set of points. You get only the intersection points of this grid. For example, this point is B1 plus 3B2. You can take B2 3 times and then add B1 to it. And the same lattice can be described by different bases. So this red basis in the picture is a basis for the same lattice defined by the blue basis. And the complexity of solving a lattice problem depends on which basis you are given. If you are given a shorter basis, problems become easier. If I give you a long basis, a basis with long vectors for the same lattice, then the basis has bad geometric properties, and that's the source of computational hardness. Now, there are two main problems that are studied in this area. One is called the shortest vector problem. You are given a lattice described by a basis, and you want to find the shortest non-zero vector in the lattice, which, as you can see in this picture, is not necessarily one of the two basis vectors. You might have to take some combination of the basis vectors to find the vector with the smallest possible length. And another problem is the closest vector problem, CVP, where you are also given a target point T, and you want to find the point in the lattice which is as close as possible to the target. Now, most of what I'm going to talk about today applies both to the shortest vector problem and the closest vector problem, but for brevity I will be talking only about this one, about the closest vector problem. So if you're interested in the shortest vector problem, you can find something similar in the papers and publications. Okay, so these are the two problems. So let's move on to the other ingredient of my talk, proof systems. You already heard from Thomas, the GMW graph tricoloring. So I'll describe actually only the problem here, not the proof system. So there's a prover and a verifier. What is a proof system? Is a method for a prover to show to the verifier that a certain statement is valid. For example, the statement may be that this graph is tricolorable. You can color all the nodes with one of three possible colors in such a way that any two nodes which are connected by an edge have different colors. And the simplest way to prove it is to release the coloring. You can tell to the verifier how to color each node, but in a zero-knowledge proof system, you can try to hide the coloring. You can convince the verifier that the graph is tricolorable, but without revealing the coloring. So this is an interactive process where the prover and the verifier exchange messages, messages that are chosen at random, at least by the verifier, at the end of which the verifier knows that the graph is tricolorable, but has no information whatsoever about the tree coloring. So what I want to talk about is proof systems for lattice problems. And so this is interesting for various reasons. One, historically, proof systems have been useful to understand the complexity of problems, of computational problems in general. They played an important role in the development of computational complexity. And they also have many direct applications in cryptography, especially zero-knowledge proof systems. For example, they can be used to design identification schemes. They can be used for proofs of plaintext knowledge. When you want to reveal, you want to convince somebody that you know how to decrypt a message, but without giving out the decryption. And they can be used in secure computation, group signatures, anonymous credential systems, and many more. So my plan is to talk, so this talk will be focused mostly on the early work in zero knowledge for lattice problems, which gives a nice setting to explain the many ideas that are also found in many other subsequent constructions. So what I'll do is to talk about the very first proof system for lattice problems that was designed by Goldrake and Goldwasser in the year 2000. And then move into another proof system of myself and Vadan, where we addressed some efficiency issues that are important for applications. So the first work was motivated by complexity issues, understanding the complexity of the lattice problems. And this second proof system was motivated by developing at least the theoretical applications where you could use the proof system in an actual protocol, and something that is important in that setting is to have an efficient way to implement the prover strategy, which is not something that is part of the basic definition of a proof system. So I will sketch how to use this proof system to build zero-knowledge identification schemes and proof of plain text knowledge. And at the very end, very, very briefly, I will mention some of the recent work. There's been really a lot of work in the last year or so on zero-knowledge proof systems for lattices, motivated in part by all the applications of zero-knowledge in various areas. And there's really a lot there are many developments going on which fall pretty much in two categories. One is designing zero-knowledge proof systems for lattice problems. So you have a problem about lattices, you want to prove something about lattices. For example, if you encrypt something using a lattice-based encryption scheme, then you may want to prove that you know the underlying plain text. And there are also zero-knowledge proof systems where you use lattice assumptions to prove arbitrary statements, not necessarily about lattice problems. In principle, you may want to give a zero-knowledge proof system for any statement in NP that can be implemented efficiently. So, first work. So this GG Goldrake-Goldwasser proof system it was motivated by this gap between the factors for which we know how to prove that lattice problems are NP-hard and those required by cryptographic applications. In particular, cryptographic applications required inapproximability, hardness of approximation for polynomial approximation factors. Polynomial in what? In the dimension of the lattice. In the picture I was only showing two-dimensional lattices, but for security the dimension of the lattice is the security parameter. So in practice you typically work with lattices in dimension that is a few hundreds, like 200, 300, up to a few thousand, depending on the application. And NP-hardness results are way far from there. They are all for subpolynomial factors, and in fact, typically this factor is just a constant independent of the dimension. So the question was, is there any hope to push these NP-hardness results for factors that are potentially useful for cryptographic applications? And there was already some result of this type. For example, if you can show that lattice problems for a certain approximation factor are in the intersection of NP and co-NP, then they are unlikely to be NP-hard, because that would collapse NP and co-NP to the same complexity class. But the factors for those results were at least linear in the dimension of the lattice, which is pretty much what we can use to build the cryptographic functions. And so Shafi and Odette Goldrake, so they came up with a negative answer to the question, can we prove NP-hardness results for factors that are as large as n? In fact, they gave evidence that there is no NP-hardness result for factors that grow with the square root of the dimension. In order to do that, they put these problems, SVP and CVP, in the complexity class SZK, statistical zero knowledge, which we know is unlikely to contain NP-hard problems under standard complexity assumptions. Okay, so how does this proof system work? So I tried to keep most of the talk with pictures, explaining the concept with pictures. I am oversimplifying a number of issues, but I hope that the pictures give the main ideas. So let's say that you have a lattice L, the set of black points here in the picture, defined by a basis, and you're also given a target point T, and you want to prove that this target point is far away from the lattice. So how can you do that? So it is not clear how to do it in a non-interactive way, how to write down an NP proof. In fact, we believe that there is no NP proof for this language when the approximation factor is small enough.
So just for people who are from, who maybe don't know these languages, there are no short proofs.
Short proofs, yes, yeah. So there are no short proofs, okay. Proofs that you can write down, then read and check. So you can try to go beyond this barrier by using interaction and randomness. And you can proceed as follows. First, you take this target T, and you copy it all over by shifts that are defined by the lattice. So you consider the set T plus L, a shifted copy of the lattice where the shift is given by the target. Then you consider two possibilities. So the verifier is going to flip a random coin and decide to either choose the set of lattice points, the red points here in the picture, or the set of shifted lattice points, where the lattice points are shifted by the target T. So once the verifier makes this random pick, then it will choose a point that is either close to the first set of points, so anywhere in these circles, in these red circles in the picture, or it will choose a point which is close, which is inside the blue circles. So it will decide to be either here or there, and then it chooses a point that is close to one of these two collections of points. It sends this point to the prover, and the prover has to guess if this point was picked from the red circles or from the blue circles. If the prover can come up with the right guess, then the verifier will take it as evidence that T is far away from the lattice, and I will illustrate in a moment why that provides some evidence. Now it's clear that the prover can always guess this bit with probability 1/2, so for this to provide substantial evidence you need to repeat this proof system a number of times, so you may repeat it say 100 times, after which you know that X set with probability 2 to the minus 100, the point is indeed far away from the lattice. So what makes this proof system work? Now, so these are the two situations. So in one case, the shifted copy of the lattice is done with a shift which is far away from the lattice. And if this is the case, then the red circles and the blue circles are disjoint. So when you pick a point from one of these circles, the prover, given unlimited computational power, assume that the prover is all-powerful, the prover can check, for example, by exhaustive search, if it came from a red circle or a blue circle. On the other hand, if that's not the case, if the target point is close to the lattice, then the blue circles and the right circles will have a substantial overlap. They will have a big intersection. So if the verifier picks a point from one of these circles, with high probability will be from the intersection of the two circles, of the two disks. So the prover will have no way to determine if the verifier started from a red circle or from a blue circle. And that's what makes the proof system correct and sound. Correct when the target is far from the lattice, the prover has enough information to determine where the challenge point came from, while in the other case, soundness, if it is not far, if it is close to the lattice, there is a big overlap. Now, an interesting observation is that this proof system is also zero knowledge, and it is zero knowledge because the verifier is just getting back his random bit. So when we are in this world, the verifier picks a random bit B and see that the prover knows the bit that the verifier already knew to start with, so it's not really learning anything new. Okay, so there are some efficiency issues. So this is useful to establish that the problem is in this complexity class, statistical zero knowledge, so it is unlikely to be NP hard. However, if you want to use it in cryptographic applications, this doesn't quite give... so there are several efficiency issues that need to be solved. One, which is a very simple one, is that I said that the verifier is picking a random lattice point and then adding some noise to it. And the lattice is an infinite object. So what does it mean to pick a random lattice point? So of course you cannot pick it from the entire lattice uniformly at random. Now, the way this was originally solved was by taking a big ball or a big cube containing many lattice points and approximating the entire lattice with a finite subset, but there is a simpler way to address this random picking problem, which became pretty much standard in lattice cryptography, and this interactive proof system is one of the first settings where this trick that I'm going to describe was used. So another efficiency issue is that each time you repeat this protocol, the verifier is only getting one bit of confidence that the point is far from the lattice, so it needs to be repeated many times. So is there a way to design better proof systems where you execute it only once and the verifier knows with high probability that your point is either close or far from the lattice? And the last one is that the prover in this proof system needs to figure out if the target comes from the red or blue circle, if it's close to the lattice or close to the target. But that's exactly CVP, the closest vector problem, a problem which we believe is hard. So it's something that requires a lot of effort to solve. So I'll go over these 3 points in a sequence and show how to address them. So the first one is this issue of what does it mean to pick a point at random. So you can do something completely different. Instead of picking a point at random, what you do is to look at the displacement of a perturbed lattice point inside the fundamental region defined by the lattice. So you can think of cutting your space into cells and then stacking up all these pieces of paper one on top of the other and just looking at the displacement of your error vector within the fundamental region of the lattice. So this has the effect of forgetting which lattice point you started from. So it is perfectly equivalent to starting from a completely random lattice point. And so this mapping, so you can define just a deterministic function that takes a small error vector and reduces it modulo the lattice. That is, it takes only the displacement of this point inside a fundamental cell. Now, if the set of lattices that so this is something you can do for any lattice. But if you take the specific family of random lattices that was used by ITAI to prove average case hardness, you get a very nice way to describe this function. So ITAI's lattices were defined not by a random basis, but by a random, what in theory is called the parity check matrix. So the lattice is defined by a random matrix A with entries that are integers modulo Q. And the lattice is the set of solutions, of integer solutions to the system of equations AX equals 0 modulo Q. So the set of solutions is a lattice. You can also compute a basis if you want, but most applications don't need that. But there is a useful correspondence that reducing a point, an arbitrary point x, which may not be in the lattice, reducing it modulo the lattice is exactly the same as computing a matrix vector multiplication. If you compute AX modulo Q, this will be 0 if x belongs to the lattice and non-zero if x is not in the lattice. So this gives a nice, convenient way to compute a one-way function based on the closest vector problem. Now, so this picture is a bit misleading. This is not quite ITAI's function. You can consider 2 versions of this function depending on how big x is. Now, if x is, so if the error vector, the input, is small enough that when you reduce in modulo the lattice, the result is always different. So if the function is still injective, then, so this is the learning with error problem introduced by Regev in 2005. And ITAI could prove hardness of these problems only when the error vector was large enough that when you reduce your input modulo the lattice, or when you multiply your vector x by a, you end up covering potentially every point in the fundamental region of the lattice. So in this case, you have a surjective function. So the function is essentially the same. It is the same problem, but for 2 different values of the parameters of the error, large error or smaller error. And the fact that here the function is surjective and here is injective enables different classes of applications. So there are many more applications based on injective functions. For example, encryption can more easily be built from injective functions. So let me mention a few cryptographic primitives that can be built pretty much in a direct way from this function, from this simple lattice vector multiplication, so you have a sense of how lattice cryptography works. So you can build collision-resistant hash functions. So this function not only is one way, not only is hard to invert, but it is even hard to find collisions between two different inputs. So here you would be using Lattice version of the hash function, which is surjective. It compresses the input, and it was observed by Shafi, Goldrake, and Halevi that you can also prove that finding collisions is hard. And that's already a much more useful cryptographic function than just a one-way function. So another simple application is commitment schemes. So you can think of a commitment scheme as a randomized version of the hash function. You append some randomness to the input. X is the value that you want to commit to. You append some randomness to it, and then you hash it using your function A. And so this commitment scheme was proposed and used to design a certain type of zero-knowledge proof system by Kawachi, Tanaka, and Sagawa in 2008. I will describe their proof system in a few slides. And encryption is very similar to commitments. So the way lattice-based encryption works is almost the same. You can think of commitments as encryption without the decryption algorithm. In both cases, you want to hide the message, and but the encryption algorithm is the same. It's only the decryption structure which is missing here. And so in so this setting, you can formulate the problem of proving knowledge of the decryption of a message, or the message underlying a commitment. So, and proving that you know the message X underlying a certain commitment is exactly the problem of proving the knowledge of a solution of a system of equations of the form AX equals Y, which is exactly the parity check formulation of the closest vector problem. So all of these reduces to giving proof systems, possibly zero-knowledge proof systems for the versions of the closest vector problem. Okay, prover efficiency. Prover efficiency is critical to use the proof system in an application, so you can run the prover on a computer. And so the idea is, so the GG proof system didn't have efficient provers, and most likely there is no way to make the prover efficient. So in order to get prover efficiency, you need to come up with a different proof system, perhaps for a not exactly the same problem. So what you can do is the following. Instead of proving that T is far away from the lattice, let's say you want to prove that T is close to the lattice. And now that the statement is the opposite, proving that it's close to the lattice, you may assume that the prover knows the lattice point close to T. And this lattice point close to T is what plays the role of a secret key in a cryptographic application. And that's what will make the computation easier for the prover than for the verifier and achieve security in the cryptographic applications. Another question is, can you come up with a proof system to show that T is close to W, but without revealing W? You want to prove in zero knowledge that T and L and the lattice are known. This would be a public key or a publicly known commitment, and you want to prove knowledge of the lattice point close to T. So this is direct applications in identification schemes and many other simple applications I mentioned before. So you could use this pair, a lattice basis B and a target T as your public key. The lattice point close to the target is your secret key, and you can put this public key on a server that uses that as your identity. In order to identify yourself to the server, you prove knowledge of a lattice point close to T. And if this is indeed a hard instance of the closest vector problem, you will be able to do that, but other parties that don't know your secret key, don't know the lattice point close to the target, will be in a hard position to prove that statement. Moreover, if the proof system that you use to show knowledge of a nearby lattice point is zero knowledge, then an adversary that observes the exchange of messages, or even an adversary that is impersonating the server and is talking to the prover, will not learn anything from the interaction, so your key will stay secret, and the adversary will not be able to impersonate you even after observing the interaction. Okay, so let's get to the second proof system. So this is a proof system to show that a target Y is close to the lattice, and it works roughly as follows. So again, we pick either points close to, so we pick both points that are close to the lattice and points that are close to the target. And since we are going to reduce them modulo the lattice, you don't need to copy the target many times. You can simply reduce these points and bring all of them inside the fundamental region. So the verifier will, sorry, the prover will pick, say, 2k points. Half of them are from B and half of them are from around Y. And then the verifier will send a challenge bit. So this time it is the verifier reveals the bit. Before it was kept secret and the prover needed to guess it. And the verifier essentially is asking to the prover to show that either the number of lattice points in the red sphere and green sphere is even, or both numbers are odd. I mean, the sum of these two numbers adds up to 2k. We have a total of 2k numbers, so we'll have so the number of points that are close to one or the other point will be either both even or they will be both odd, these numbers. And the prover claims that these two numbers can both be even at the same time or odd at the same time, which is only possible if there is a point in the intersection of the two spheres, modulo the lattice. But the only way for the two spheres to intersect is for the target to be close to the lattice. So being able to answer both questions shows, so the only way to be able to answer both questions is that the lattice point is close to the lattice. So I hope this is sort of gave the intuitive idea. So, but I'll describe now a different way to present these two proof systems, but described at a different level of abstraction in terms of commitments. So commitments that were already described a number of times today is a method to take a message inside an envelope. You can seal it. The commitment has two properties. A secrecy property that says that when the envelope is closed, you cannot tell what's inside. So if you are putting a bit inside this envelope, you cannot tell if the bit is 0 or 1. But at the same time, the commitment is binding. Once you close the envelope, there is no way to change the message bit which is inside it. Now, the closest vector problem I described before gives a very special type of commitment, which is both perfectly binding and perfectly hiding, which is not possible in general. You cannot achieve both properties at the same time, but you can achieve them in the following sense. So think of these two sets of circles. Remember, the red circles and the blue circles. Of course, this is implemented using reduction modulo the lattice, but this is probably easier to visualize. So think of picking a point from the red circles as a commitment to 0, while picking a point from the blue circles as a commitment to 1. So these are the way you commit to 0 and to 1. And now notice, if the target point is far away from the lattice, this commitment is binding, because the blue and red circles are disjoint, so commitments to 0 and commitment to 1 are completely different. On the other hand, if the lattice point is close to the lattice, the commitment scheme is hiding. So the circles overlap. In the limit, if the target belongs to the lattice, the circles are the same. So the commitment scheme will hide the bit, because commitments to 0, red circles and blue circles, are essentially the same distribution on perturbed points. So you have this is called an instance-dependent commitment, because the details of how you compute the commitment value, it depends on the CVP instance that you are given. You are given a lattice and a target point, and then depending whether it is an instance where the target is close to the lattice or far from the lattice, the property of the commitment are different. Now, so we know that these two properties hold true.
So in other words, you're saying that if the statement is true, it will be binding. And if the statement is false, it will be hiding.
Yeah, so it depends if you are thinking about your proof system or my proof system. So, okay, so you can describe both proof systems in terms of this commitment function. And so in your proof system, what you are doing is exactly picking a random bit, then committing to the random bit, sending it to the prover, and the prover has to guess which bit it was. So it has to break the hiding property. And by breaking the hiding property, it is showing that the target point is far away from the lattice, because when it is close to the lattice, the commitment is hiding. Okay? While in the proof system with efficient provers, so you are sending a commitment to 0. The prover is sending a commitment to 0. Here I am oversimplifying, considering a single message rather than 2K. But, so you can think of sending a commitment to 0 or just any fixed commitment, and then the verifier asks to the prover to either open it to 0 or to open it to 1. And the prover will be able to answer both questions only if it can break the binding property of the commitment scheme. So in this case, by breaking the binding property, by showing that you can answer both questions, you are showing that the target point is close to the lattice. So, Shafi, which of the two of these two things were you?
No, it's a good point, because I sort of forgot for a minute that what you are showing is the closeness, not far.
Yeah, so I don't know.
You're showing closeness in zero knowledge, right?
Yeah, they are both zero knowledge. So both proof systems are zero knowledge.
One of them you're showing far, and in the other one you're showing close.
Yes, yeah. Mm-hmm. And okay, so you are using the same underlying instance-dependent commitment based on the closest vector problem, and you get different properties that can be useful for different purposes. Now, there is one last issue that is, so this still, even today, a gap for certain type of efficient proof systems from lattices. So there is a gap between what you need to know to show that a point is close to the lattice and what you are proving to the verifier. So in the previous proof system, sorry, this is typo. This should have been a P. So so you are showing that this point P is close to the lattice, and it is also close to a shifted copy of the lattice. In both cases, it could be within distance beta. Now, by triangle inequality, it follows that the distance between T and the lattice is at most twice beta. Moreover, in order to get a zero knowledge property, beta has to be quite a bit bigger than the distance between T and L. It has to be bigger roughly by a factor square root of n. So the prover needs to know a point within a certain distance, x, and it is only proving that the target is within a distance bigger than that by some factor. So there is this knowledge gap between what the prover knows and what the prover is able to show he knows, that has an impact on the practical, concrete efficiency of zero-knowledge proof system, so reducing this gap is useful. Now, there is a way to reduce this gap, and this is what was first done for a variant of CVP by Kawachi, Tanaka, and Sagawa. This is the paper I mentioned before, where they suggested to use lattices to build the commitment schemes. And what they did in that work was to adapt a previous zero-knowledge proof system for coding problems that was suggested by Jacques Stern some 10 years earlier. And they show that it can be adapted to certain versions of lattice problems. In particular, consider a lattice problem where the error is a 0-1 vector which is perfectly balanced. It has half 0 entries and half 1 entries. And the proof system works by the prover committing to 3 different messages that are built from a random permutation, is a permutation of the coordinates of your vectors, and a random vector R, which is given as an alternative secret. It's not the error vector that you want to prove is short, it's a randomly chosen value R. Then it also commits to a permutation of R, and it commits to a permutation of X plus R. Now, this is a little bit technical, but if you just work on it, any 2 of these messages do not reveal anything about X. I mean, it is clear that these 2 don't reveal anything about X because X does not even appear there. But if you look at these 2, for example, they also hide X, because from these 2, all you can recover is the permuted version of X. And since x is a balanced vector with half zeros and half ones, when you take a random permutation of it, you get something which is completely uncorrelated with x. It's a uniformly random error vector from that set of balanced binary vectors. So this was useful already for some applications, but if you think of it in terms of lattice problems, you would like to solve this problem for short vectors, not vectors which are bound to satisfy this constraint. So you would like vectors that belong to a ball or a cube or some other regular geometric structure. And so this is something that was achieved by Ling, Yen, Stelle, and Wang a few years later, which showed essentially how to reduce the problem for the L infinity norm. So if you want to show that all the coordinates of the error are at most beta, so you can take this problem and turn it into one that can solve using the TKX protocol I showed a moment ago. So their proof system was introducing again a knowledge gap. There was a factor 2 between what the prover knows and what the prover is showing to know, but that can be easily so it can be easily removed. So there's a variant of this proof system suggested by M stands for myself. And it works. So this variant works as follows. So you want to show that all the coordinates of x are at most beta, that is, they are in the interval minus beta to beta. So first you can shift it to be all positive by adding beta to all of them. Now you want to show that all the numbers are between 0 and 2 beta plus, actually without a plus 1. So it would be only the 2 beta here. But there are 2 beta plus 1 possible values. And then you can try to write all the numbers between 0 and 2 beta. You can find a collection of numbers, alpha 1 to alpha 2k, such that all the numbers between 0 and 2 beta can be written as a subset sum of these numbers, and not only as a balanced subset sum that has exactly k elements equal to 1 and k elements equal to 0. So this is very easy to do when beta is a power of 2. You just take the powers of 2 and you write the binary decomposition of your numbers. And at this point, you just want to show knowledge of a binary balanced vector, which can be done using the previous protocol. So I'll quickly okay, good, thanks. So there is another class of protocols, zero-knowledge protocols, that addresses the issue of knowledge error. So the protocols I showed before, so this one, there were 3 possible... So this one, so the verifier was asking to open 2 out of these 3 commitments. So every time you execute it, there is only a constant probability that it will catch the prover cheating. So you need to repeat it a large number of times. Now, there is a different type of protocols which follows the approach of the Schnorr identification scheme that, if you were at the other workshop yesterday, was described by Dan Bonnet. So that one was for discrete log-based proof system. There is a way to adapt it to lattices. And so you want to show knowledge of a vector x to a solution of ax equals 1. And you can do that by sending AR for a randomly chosen R. And when you receive a challenge C from the receiver, you reveal a random combination of X and R. And since now C can come from a large set, a potentially exponentially large set, and the prover can only answer one of these queries without the statement being true, it will immediately achieve a soundness error, which is 1 over the possible choices for the vector for the challenge C. However, this proof system introduces again a type of knowledge gap, because so the soundness rests on these 2 properties. Assume that the prover can answer 2 challenges, C prime and C double prime, and it can give you short vectors, X prime and X double prime, satisfying these 2 equations. Now you can combine them together, and you get a small solution to the system AX equals not quite Y, but equals CY for some constant C. So the prover is showing not knowledge of a pre-image of Y, it is showing knowledge of the pre-image of a multiple of Y. And in this discrete log setting, you can just divide everything by C. But in the lattice setting, where you also want numbers to be small, you cannot do that. If you do division modulo Q, numbers from small they can become very big, so you cannot quite do that. Now, this proof system was used as the basis of a number of digital signature schemes, starting from the one-time digital signature scheme of myself and Lubashevsky. And one property of the scheme is that it didn't require random oracles, so it was standard security, but it only allowed to sign one message. Now, if you replace the fixed query with a random oracle, then you can get schemes that can sign an arbitrary number of messages, which can also be improved and optimized in various ways. And this is this technique called the Fiat-Shamir without bursts that was used to design a sequence of more and more efficient lattice-based signature schemes, some of which are some of the candidates to the current NIST post-quantum cryptography standardization process. So I've just to last slide where I'm just mentioning some recent results. One of them is about using lattices to design non-interactive zero-knowledge proof systems. And this was first done in 2008 for lattice problems. So this is something that's been known for a long while, and the question was, can you give lattice-based proof systems, not just for lattice problems, but for arbitrary problems in NP? And so there were some various types of partial results giving solutions that are not quite non-interactive zero-knowledge, but they are restricted forms of zero-knowledge. And this problem just got solved very recently, a month ago, by Pikert and Sheshan, that gave a non-interactive zero-knowledge problem from the standard LW assumption for all of MP, building on some recent previous work of Canetti and others that already had a framework with some more complex assumption that was turned into a standard lattice LW assumption. And so there is much more recent work that I don't have the time to talk about, but just to give you a sense, this is a sample of papers on lattice zero-knowledge from this last year, giving zero-knowledge proof systems for specific problems, methods to achieve sublinear complexity and properties for arbitrary arithmetic circuits. Something which I think is very interesting is this work of Delpine and Lubashevsky, where what they do is to prove properties of lattice-based crypto systems, but using discrete log assumptions. And they make an argument that even if you want post-quantum security, so this system is achieving statistical zero-knowledge, and it is achieving soundness under pre-quantum assumptions. But soundness is something that you check right away during the interaction. So even as long as quantum computers have not been built yet, you can use it. And if somebody stores all the interaction to break it when quantum computers are built, well, there is nothing to learn from that because the system is statistical zero-knowledge. So it's a nice combination of the two techniques which could...
So it's an interesting idea in general, right? To build things that today work, even without quantum computers, but are safe for later. Yeah.
Yeah, especially because so in properties that are interactive, you need to break it right away. I mean, it's, you cannot postpone the interaction later on. Well, of course, for non-interactive zero-knowledge, it is different. But yeah, so for the interactive version of the protocols, you don't need the post-quantum security until it is too late.
Reason for interactive protocols.
Yeah, it buys you more. There are other properties that you get from interaction. You can get forms of deniability and methods that, to avoid the proofs being transferred. But yeah, interaction is not always negative. It can also be a useful feature. And this concludes my talk. Thank you for your attention.
Any questions? Okay, so we'll move on, and now